So our example of Biocybernetic Loop was an adaptive version of the game Tetris that was running on EEG. So the way that the system worked is that we had two channels of EEG being collected from frontal sites and parietal sites, and we had these being analysed in real time. And then we had a connection with a version of Tetris to make the game run from it. So what I'm going to do is describe the 6 different phases that we went through in order to develop this loop. We basically built a conceptual model to understand what the system was meant to do. Then we built up the inference between the EEG and the data and made a quantified model of the user state, which turned into a real-time model. Then we designed the interface, and then most importantly we evaluated the system. So to begin with, we wanted a sound basis for the system to be developed. Now there's 2 types of conceptual models that we could think about. One is a psychological model, and this psychological model would represent the distinction between different psychological states. And the other type of model is what I call the rationale for the loop. So it's a statement of which states are to be detected, and then how do we map those states onto a functional vocabulary system? How do we make a relationship between the different states that are measured by the system and what the system actually does? So we began with a conceptual model. Now this is a model from social psychophysiology called the motivational intensity model. It's quite easy to understand, I think, is that basically you have, it describes a relationship between the level of effort that people put into the task and the level of demand of a task. And what this model argues is that people will increase their effort as a task gets more difficult up to a certain point, whereupon they feel that they are not going to succeed at the task, or they feel that the task is no longer worth persevering with, and then effort falls from that point. Now this model has been assessed in laboratories using cardiovascular data. It's been assessed using blood pressure mainly and related measures. So what we wanted to do is say that if we've got a Tetris game where we're making the game more difficult by increasing the speed with which the blocks fall, we are taking people up to this loop, and what we want our game to do is to keep them in a place where they are interested in the game and enjoying the game. So we have what we describe 4 different zones associated with the way the player might play the game. We have boredom, where the player is not interested at all, the task is too easy. Then they get more and more engaged, up until a point where they're overloaded and they give up. Well, this point here, this point here is what we call the zone. We assume that most players want to be at a point where they are very challenged, but they are not in a position where they are failing all the time. And we want to keep the players there in that particular area. So, so that was our conceptual model that we based our system on. But as I said, the model has been developed mainly, almost exclusively with, with cardiovascular measures, and we wanted to use EEG. The other thing to say about the model is that what this tells us is that our biocybernetic loop should be pushing people up towards the zone and pulling people back from the zone. Now, so we begin really with, well, what measures can we have? We want measures that are sensitive, and we want measures that are valid, and we want supporting evidence from the literature. So we want to test the measures in the context of system operation. Now, this really goes back to your question earlier, is that we've got a lot of data here on people using psychological tests like working memory tests and so on, and measuring cardiovascular measures. And there are experiments that show that. But what happens when you want to play Tetris, which is a completely different scenario? Do those results generalize over? So what we did was that we constructed an experiment where we had an easy, a high and a very high version of Tetris. So an easy version of Tetris, a challenging version of Tetris, and a version of Tetris where the shapes drop so quickly you barely have time to respond. And we measured EEG. And what you're seeing here is EEG from the theta range, which is between 4 and 7 Hertz, and we are measuring this from an area called FZ, the frontal central area, which is about here. So this is a nose that you can see on the bottom. And you can see that theta intensifies as the task becomes very hard, and then theta falls again when the task is impossible to do. What we also did, we measured alpha activity, which is the EEG activity in the range between 8 and 12 hertz from the parietal area, which is kind of around here. And we found that alpha gets more and more suppressed as time goes by. So you just have this curve that kind of goes downwards. So once we did this experiment, we knew that we had measures that were sensitive to Tetris, and they worked within the manipulation that we wanted to use. So once we have the model, and once we have the measures, and we've tested the validity of the measures, we can then quantify this, this conceptual model. So this stage of the design cycle is concerned with operationalizing the user states. So looking at the accuracy and the fidelity of the user model, and then trying to measure it within the context of system adaptation, which is what we just did. So it's important within this stage to understand what the system will actually do and how it will interface with the adaptive rules of the system. So for our system, we used two measures. As I said, we used theta from FZ and alpha from parietal P4, which is in the parietal area. And this is a hypothetical example of what the relationship with them looks like over 3 different levels of game difficulty. So what you see is that theta initially rises and then it falls when the task becomes impossible, whereas alpha just declines all the way through. And so what we did then is that we map our 4 levels of user state onto theta activity and alpha activity. So if we begin with this state here, with the boredom state, what you see here is that alpha is very high and theta is very low. So this means that the person is kind of quite bored at this point. But if theta starts to rise, then we get into the engagement area where we have, you could have high levels of alpha, but we have high levels of theta. And this is an area that we would want to push the difficulty up. When we have low levels of alpha and high levels of theta, we are in the zone. This is the desirable place where we want the player to be. And then when we have, when theta begins to fall, whilst alpha stays low as well, we have overloaded the player. So we've basically deduced this from running the experiment beforehand and understanding the relationship between our two key measures. Now, the quantified model of the user that I've just used describes a data space of the biocybernetic model, but we must transform this quantified model into a real-time model in order to use it with the game. Now, traditional laboratory experiments don't really explore this aspect. Traditional laboratory experiments are based on group means and they're analysed retrospectively. So for someone who's trying to design a game, the challenge is in creating this dynamic loop is being able to develop a loop that delivers a classification that's both timely and accurate. And so first of all, the first thing to think about here is that the data must be filtered or it can be corrected for artifacts. So there is an issue of lag. So you're collecting data from an EEG. When you put a filter on an EEG, you create a lag in the system. If you introduce any other processes, you create another lag on the system. So whether this is a problem or not depends on the relationship between the maximum window permissible for software response and the minimum window for the loop to create a meaningful data analysis. If the minimum period for analysis exceeds the maximum period for the meaningful response, then the model will be able to respond in a timely fashion. The other issue is data classification, or how triggers are derived in order to initiate system responses. So there are several different ways in which you can classify data, ranging from simple threshold values, which is what we used in this, to the type of heuristics that John was just describing, to fully formed kind of statistical models based on machine learning techniques. These models all have one thing in common, is that they need to be trained beforehand on representative data samples. And so we need to train it on data that is based on the thing that they're actually going to measure. In terms of how you train it and how you measure it, people use different approaches. Some people use subjective self-report accuracy. And this is a good logical choice because the way that the system responds, as I said in the first presentation, must correspond in some way with the subjective experience of the person. Now, for our particular example, we decided that we were going to measure the activity of theta and alpha. And in order to do this EEG analysis, we needed to filter the data, we needed to do an FFT on the data. So we felt that a 5-second window was a reasonable window that we could use. And this is always a difficult decision to make if you're making a real-time system. If you make the window too short, then you get lots of fluctuation, lots of variability. If you make the window too long, then you get stability, but the system may not be able to respond in time. So designing the time windows is kind of quite important, I think. So we ran a calibration session initially. We had people play Tetris at 10 different levels of difficulty for 2 minutes, and then we asked them to indicate what their preferred level of difficulty was. This didn't work out at all, because some people just chose the easiest level of difficulty because they wanted an easy life. And the fixed level of Tetris was basically unrepresentative of what they were going to do during the game. So in the end, we chose an absolute criteria based on baseline levels of alpha, theta and alpha. So we had our participants watch a relaxing movie for 5 minutes, and then we recorded EEG levels, and then we defined a change of theta as being 100% plus or minus the baseline, and a change of alpha is plus or minus the baseline that we collected when they were watching the movie. Now, in many ways, this is very far from perfect, and I'm presenting this case study to you not as a perfect case study, but as a kind of as the lessons that we learned through going through this process. The next thing was actually designing the interaction of the interface. So we know what we're supposed to do, but how do we actually make that happen at the interface? Now, if you're designing an input control system, say it's a mouse or a brain-computer interface, you have the mapping between what happens when the person thinks about moving, what happens on the interface, is quite explicit and open. For these type of biocybernetic adaptations, the link is not so clear. The link is very open to interpretation. So what we decided to do was that we had the options that I mentioned in the last presentation of explicit and implicit adaptation. So we had the options of changing the Tetris by an awful lot, making a big change in Tetris, and we could also show people a level of Tetris on the screen. And we experimented with different forms. And what we decided to go with in the end was to go with an implicit adaptation. So we changed the Tetris a lot, very small changes to the Tetris over the period of time, and we did not tell people what was going on. So effectively, when you played the Tetris, you had to play it for maybe a minute or so before you worked out which direction if you were being pushed or pulled in a different direction. So we had no explicit feedback. We decided to make the adaptation quite small, so we made a minor rather than a major adjustment to drop speed. And so what we have done is created a system which, rather than having big discrete changes to make things happen, relies instead on a successive series of small changes in order to gently push the momentum of the person in a certain direction. And this is an example of the rules of the system mapped onto the actual measures. So basically, if the system determined that people were in the green zone, where alpha was falling and theta was rising, then it would increase the speed of Tetris. If it assessed that they were in the red zone, where alpha was falling and theta was falling, then it would reduce the speed to try and pull them back into the safe zone. And if they were in a space where neither were changing, were in the middle, then we did nothing. So this is where we try to keep them in that particular space. So once the system's been designed and it's working, this is a really important point, because when we make these biocybernetic loops, we want to show that the biocybernetic loops are actually working, they're actually beneficial. But the question then is, what is benefit? What do we compare it to? And so what are the criteria for evaluation? So we have to think very carefully about how we evaluate this type of system. We can look at benefits such as enjoyment or efficiency or performance. Some loops we want to reduce mental workload, or we want to reduce stress and frustration. But what we have here is that these two things really is that if you have a version of Tetris which is acting on brainwaves, what do you compare it to? Because comparing it to the normal static Tetris is not really a fair comparison. Also, because you have EEG and you have all these sensors involved, there's an enormous issue of novelty, and people tend to approve of novel things and say, yes, this is good, because they've never experienced it before. So there's two things to think about here, is what you compare it to and how long you conduct the evaluation over. What we decided to do was to look at different versions of the adaptive Tetris in order to understand what was going on. And in terms of measuring what was happening, we measured performance on the game, how many times they died in the game, and those sorts of things. But we also measured mood as well. So what we did in the end is that we prepared 4 different versions of our system. Sorry, that's wrong. So we had a manual system where the person just said up, up, down, 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 so they could then basically move the Tetris to a space where they wanted it to be. And then we have our normal system, which is 100% change, is when it actually makes an adjustment. And then we had a manual system, a liberal system, which gave more frequent adaptations, and a conservative system, which gave less frequent adaptations. And 10 players played on each version, and we measured mood as well. Let me show you how the systems worked. This was our normal system. So if there was a deviation in theta or alpha of 100% on either side, then we said this is a change. We compared that to a more liberal system, which would basically make adaptations when much smaller changes in EEG occurred. And we compare that as well with a more conservative system, which only made a change rate to change by 200% or more. So in order to evaluate the system, we evaluated the system with different versions of itself, really. And then this is what the results came out like. So I don't have the mood data on here, but if we just look at the, first of all, look at the manual system. So the reason we did a manual system was we don't expect it to be adjusted with the same level of frequency as the other systems, because obviously people are telling us to do this. So people would just adjust it upwards until they got it to where they wanted it to be, and then they left it there. But what this tells us is that most people wanted a game demand around 3.3 out of 10, so they wanted quite a low level of game demand. Sorry, just a sec. Okay. Now if we look at the different versions of the system. So our basic system made the game more difficult 42 times over the course of this. This was much more than the liberal system, but much less than the conservative system. Our conservative system tended to push people up higher more frequently. The basic system and the liberal system tended to result in many more decreases of difficulty. So as you can see, the level of difficulty was kind of on the low side, and people did not enjoy these games as much as they did the manual game, where they'd adjusted it themselves. But you can see the level of times they died in the game is roughly the same between these. The conservative system was interesting because it tended to push people more than somebody else, it tended to do fewer downward adjustments, it tended to kill people more frequently, and it tended to push people's game demand above what they would be more comfortable with. And what we found was that this was the level of game difficulty that people found the most stimulating aspect of the game. But they also found it the most stressful one as well. So our solution really, I guess, was to compare the game effectively with itself. So what I wanted to take from this really is that when you're designing these sorts of loops, it's an integrated process. It's basically not just about choosing the right measures or working on data classification. It works by putting all these different pieces together. The most important part of the integration is reconciling how data must represent the user and how it represents changes in the user state, and whether that is a spontaneous emotional response or a cognitive response or whatever it is, we need to be able to have an integrated view of how the measures and the states and the adaptation all kind of work together. I hope you can see the challenges faced during this process. You can see that the challenges are multidisciplinary. There's some kind of psychology that comes in at the beginning, and then we have some maths, and then we have some engineering, and so on. So it's a multidisciplinary process. And personally, I feel that the only way we can make these systems and make these systems in an effective way is by having multidisciplinary inputs from different people. I think it is very difficult for the psychologist to play computer scientist and vice versa, and you need the teams to kind of work together in order to put all this together. And that's where I am. Okay.